ladies and gentlemen. Welcome to another Computer Science Colloquium. Next week we will not meet because it's spring break, as if I had to remind you. But after we come back from the spring break, we'll hear from Cooper Canteen, who will update us on the status of Do Not Track, as his organization, the Electronic Frontier Foundation, is trying to establish. Today I have the pleasure of introducing you to Ippolito, who's going to explain finally to all of us data structures. Let's welcome our speaker.
Thank you so much for inviting me, George. So today I'm going to talk a bit about persistent data structures. I'll get to that in a bit. We'll start off with a little bit about who I am. So I'm a self-taught programmer. I'm sure maybe some of you are, but I learned by reading books myself. I'm an open source contributor. I've written open source for Python. I wrote the JSON implementation that Python uses, among various other Mac-specific things. I've written JavaScript frameworks before jQuery existed. I've done a web server in Erlang, and I've done a little bit of Haskell stuff here and there. I'm an entrepreneur. I've founded and sold 2 companies so far. My first success was Mochi Media. I started it about 10 years ago now. We sold it in 2010, and what that business did is we built an ad network for Flash games. So like games that you play on the web, we allowed game developers to monetize it. So when you played a game, it would show an ad, and the game developer would get paid. So sorry about that, but the game developers really liked it, and it helped fund their efforts. A lot of them are very successful mobile game developers now that they've moved away from Flash. And after that, I had a quick project called Peaceable with some friends, and that was an iOS developer tool where essentially we took the iOS simulator and we made it available in the cloud, so you could use it from a web browser without actually having an iOS device. So that was very good for testing purposes. Like if I built an app and I wanted to show it to you, I didn't have to like get you to install Test Flight or any of that stuff. I could just give you a link and you could use the app in your browser. A lot of customer service organizations and stuff also use that. And we ended up selling that to Facebook, so I got to work there for a little while. My current projects, I've got 2. First one is MissionBit. We have a 501c3 nonprofit in San Francisco. We've been around for about 2 years now, and we offer free after-school coding classes. And we offer those to high school and middle school students in San Francisco right now, but of course we would like to expand. We're just not quite ready for that yet. All the classes are taught by volunteer tech professionals, such as myself, and we offer summer internships, company visits. We have a hacker lab at Mission High School, so it's just a room where we have like cool stuff like MakerBot and Oculus Rift and Leap Motion and Arduino, Raspberry Pi, stuff like that students might not have access to otherwise. And they can also stop by for help with their homework or projects or really anything computer or programming related. We help support them with that. And my current professional occupation is a company called Nom Labs. We started a couple months ago, but we're not really talking too much about that yet. But hopefully next time. So anyway, data structures. I'm sure many of you know data structures are a particular way of organizing data in a computer so that it can be used efficiently. And the key word there is efficiently. And some examples of data structures would be an array or a vector, same sort of thing. There are various sorts of maps, hash maps, associative arrays, dictionaries, and there are structures like records or tuples. They're literally like thousands of different data structures with different performance characteristics, and it's good to study them so you know which one to use, because sometimes you really need that efficiency. And so efficiency is the extent to which time, effort, or cost is well used for the intended task or function. And in particular, when we're studying data structures and algorithms, we're looking primarily at space efficiency and time efficiency. By space, we typically mean RAM. So like your very fast random access memory in the computer, whether that's CPU cache or DRAM or whatever, and also time. So that's CPU time, which is correlated to power and also the actual time it takes. And so there are two basic ways that we measure this. We measure it in theory using big O notation, which I'm sure many of you are familiar with. There are other more precise ways of measuring algorithmic time in theory as well. And there's also benchmarking, where you actually give it real data and see how long it takes a real computer to execute. And these may or may not match up because big O, you're concerned with worst case times, and you're not concerned with any of the constant factors. So whether that's 1,000 times n or 1 times n, you're not really concerned with that when you're talking about big O. So that's where the theory and practice differ quite a bit. In practice, those multiples are very, very important. But in theory, you just ignore them. And typically, you measure the worst case time, but sometimes you measure average or amortized time, particularly for randomized algorithms and such. And there are a whole lot of different big O measurements, but here are some of the common ones. There's O of 1, constant time. So that's like an array indexing operation. So you have this array, and you want to get an element out of that array at random. And that you can do that in constant time because there's no seek time for RAM, or constant seek time for RAM, I suppose. There's logarithmic time, such as binary search. You have a sorted array, and you want to find a particular element by its value. And it's logarithmic time because when you search, you start at the middle, and then you know it's either less than the middle elements or greater than the middle elements. So you get to divide the search space by 2 each iteration. And so it's log 2 of n, but we don't even care about the log base because that's just a constant factor. But that does matter in practice. There's linear time, where essentially you have to look at every element some constant number of times, such as finding the minimum element of an array, an unsorted array. So you have to scan every element to see if the element that you're looking at is less than any previous element that you've looked at. And then there's linearistic, or n log n, which would be an optimal comparison sort, such as merge sort or something like that, where it's basically logarithmic and linear just put together. So you have some logarithmic algorithm that also has to look at every element in each of those partitions. And then there are other algorithms that are even worse, such as n squared or 2 to the n or something like that. You try not to use those in practice, but sometimes you have to, and sometimes they're actually not that bad. A common example of a quadratic algorithm would be bubble sort, where you have an unsorted array and you sort it by going over it and swapping consecutive elements for order until it's sorted. And it turns out that the worst case time is pretty bad, it's quadratic, but the best case time is linear, because if the array is already sorted, you have nothing to do. You just scan over it once, there's no swaps to be done. So if you expect an array to be mostly sorted, something like bubble sort or insertion sort is actually not that bad. And so there are other things that are very important with data structures and algorithms that are less often measured and in fact much harder to measure. It's really important when you're building a real application how easy it is to use that data structure correctly. Some data structures are very easy to use correctly, others are very hard to use correctly. You've probably experienced some of this yourself. There are other features that we want these days, like time travel. So basically any sort of application that you use today, you expect undo to work, or redo, or even branching, like you're doing version control in Git. You don't get that if you're just mutating an array in place. You have to do some other bookkeeping. And it's also become very important in recent years to support multicore. So computers aren't really getting faster anymore, they're just getting more cores. By faster, I mean clock speed. So each core can't serially execute instructions much faster than the previous generation of chips. We just give them more cores so they can do more at the same time. And some data structures are suitable for multi-core use, where you can very efficiently have more than one core read or write to that data structure, and other data structures are very bad at that. So that becomes important now that even your cell phone has more than one core in it. Whereas when most of these algorithms and data structures were developed, that was a theoretical problem that they don't have yet. But it's very much a problem today, and we haven't the research hasn't really caught up to practice. So by correctness, some of the most important things you can do to enforce correctness are cheaply enforcing invariants. So the invariants are the things that you know to be true in that data structure. And with certain data structures and certain APIs, you can actually guarantee that that data structure is used correctly. It's very hard to do with something like an array where you can just mutate it willy-nilly and copy the reference and use it in multiple places, and hopefully it all works, but maybe it doesn't. And an important way to make that work is to have a referentially transparent interface to that data structure. So when you call a function on that data structure, have it being referentially transparent means that the result of that function is substitutable for that function call. So setting a mutable array is not referentially transparent because you can't just replace it with the result, because there is no result. The result is the side effect. But with other sorts of data structures, the result is the new version of that data structure, which is referentially transparent. You can replace that call with the new version without having to do any additional bookkeeping or anything like that. And so it turns out that that's much easier to use correctly because you simply can't do it wrong. And so this time travel stuff, a typical mutable data structure, you can always take a snapshot in about linear time, unless the data structure happens to be like circular or something. If the data structure is an acyclic graph, then you should be able to take a snapshot of it in linear time. But it also takes linear space to do that sort of naive snapshot. And sometimes, if there's structural sharing involved, so if you manage to do it in less than linear space, you might have problems if you try and mutate one of those versions, because that effect might propagate to all the other versions. So it's like Back to the Future. You go back in time and you stop your parents from meeting, and then the future is ruined because you mucked with the past. And so these sorts of features are important, in particular if you're doing something with branching histories where you have like a redo function, so you're versioning your code with Git, and you make an experiment on one branch, and you don't want it to affect your other branches. And for concurrency, the important bits are really the race conditions and locks. So you can always sort of fix race conditions by just putting locks around things, but then you're not really concurrent anymore, because a lock is serialization. So the data structure can't be interfaced with by more than one of these cores at a time if you're using locks. And locks also are typically quite slow, because these CPUs have to sort of fight it out to see which one of them is going to win that lock. But there are certain data structures that you can use where no locks are necessary. So these typically work much better in multi-core environments. And locks have other problems. They can be hard to compose and hard to use correctly with deadlocks and live locks, and that would be a whole other talk. So is there a solution to any of this? Well, it turns out that if you have everything be immutable, you can solve most of these problems at an acceptable cost. So immutability means that once you create an object, the state of that object cannot be changed. So you create an array, that array is fixed in time. It's const, or if you're using C or C++ or something like that. It's a constant. Like you can only lose the reference to it. You can't modify it. not directly. So the obvious cons to this immutable approach is it definitely takes more space because you can no longer modify things in place. And it can often take more time because you have to allocate this space, you also have to do something, so that takes up time. And sometimes it can be less convenient to program without the in-place updates. So here's a simple function in JavaScript here that just mutates the first index of an array. So it adds 1 to the 0th element of that array, and it returns the array, which isn't particularly useful in this case because it's returning a reference to the exact same array. So we start off with an array that is a sequence of numbers here that's almost in order, in the enumeration order of integers, and I increment it. So the pros of this approach is that it's constant time and space. You can't really do better than that performance-wise. But there's no persistence. That original x is lost. The original array is just gone because I modified it in place. I just destroyed it. I have this new array. And I can't go backwards without doing that additional bookkeeping somehow. And so this is what it started off as, and now it's this. Like the first one is just gone, which sometimes that's okay. But if I take a naive approach and I want to make sure that that original x doesn't go away, I can simply copy the whole thing, which takes a linear amount of time and space. So this function is very similar. I just essentially have one new line here where I make a copy of that array with a slice. And here, the pros, there's only one really, is that I have this persistence now. So it's referentially transparent. I can replace its result. I can replace the function call with its result without changing any of the semantics. But the cons are pretty big. I've introduced linear cost in both time and space to use this version. And we can demonstrate that here. Like I start off with x, with those 5 elements, and now I have x1. And it's a completely separate memory here, so that it's full cost. And so when we talk about data structures, we talk about efficiency. And so persistent data structures are able to do this efficiently. So it can go from this array to this array without incurring that full linear cost in time and space. And it's important to note that persistent is a great word and it's used for a lot of things. But when we talk about persistent data structures, we're talking about this immutability and referential transparency. We're not talking about disk, or we're not talking about saving it to the cloud or any of that stuff. We're talking about its semantics. And a very commonly used persistent data structure would be the Radix Tree. It has a bunch of different names. One word that you'll see pretty often is tree or try. The word isn't really deterministically pronounced. It comes from the word retrieval, so you would expect to pronounce it like tree, but people often like to say try so that you can distinguish it from this other tree word. And it's also even more confusing because these tries are a particular kind of tree. So the terminology here is awful. Oh, we could do better, but it's hard to change things that have already been said. So the interesting thing about these trees is that they can be used for array-like use cases. And specifically, we're going to look at a variant of this tree called a Patricia tree. And Patricia tree is just a very specific version of a Radix tree, such that any node that is an only child is merged with its parent. So essentially, you just don't have structure in the tree that you don't need. And here's a simple representation of a Radix tree. So you have the root of the tree, which you sort of have to have as a separate data type, because otherwise you'd have a hard time representing an empty Radix tree, at least providing an object-oriented interface to one anyway. And you have these internal nodes. And unlike a binary search tree, for example, these internal nodes do not carry any value. They're just structure. So here, this is a binary Radix tree, and you have a left node and a right node, and all the values are stored in leaves, which are like terminal elements of that tree. And simple representations of a Radix tree, like here's how I might represent an empty Radix tree with this representation. And then I add an element to it, and because you don't have nodes with only one child, we just have this leaf. And when I add another one, then it starts to build up that internal structure because it has to point to both leaves. And then you add more nodes and you add more internal structure to it, but it's just a log amount of internal structure. And in this representation, it looks like we're doing a lot to keep appending to this array, because we're creating all of these new objects all over the place. But the technique that we use to make this cost much more acceptable is we use something called structural sharing. So because all of these objects are immutable, we know that they never change over time. They're just created once and that's it. We never need to copy them. We can just reference them in memory. It's just a pointer reference. It's not a by value copy. And we'll go through that again, but we'll just elide all of the shared structure that we don't need to copy. So of course, with the empty tree, that's just what it is. So there's nothing to share. And when we add an element to the empty tree, there's also nothing to share, because we have to always create the parent node over again, because we can't mutate the existing parent node. But once we start going beyond that one element tree, you see that we can start sharing some of that structure. So that leaf that was holding A, we don't have to create that again. We can always use that A leaf whenever we're working with this structure. Because that A leaf doesn't point back up to its parent, we don't have to modify it at all. And so we add another node for the third leaf here, and you see that the entire structure for the first two leaves is shared. So we're paying very little cost to keep adding these nodes. And so here we're sharing the whole left side of the tree and sharing this C leaf here. And at each step, we allocate very little, despite the array growing to a much larger size. And here's what that looks like visually. So we start off with an empty tree, and now we have the leaf with 0 in it here. Instead of A, B, C, D, I just used numbers for this one. And I added another node here, and this is blue because it's shared. I'm not allocating anything here. And when I add another node, I don't have to allocate anything in that left branch. And you can see as it grows, more and more of that structure is shared. And it turns out that this is logarithmic time, because the height of the tree is the log of the size of the tree, log 2 in this case, because the branching factor is 2. And I only have to update those parent nodes on the way up. And the other interesting thing here is I don't have to balance this tree. It's naturally balanced. There's no sort of rotation operations like a red-black tree or something like that. And we can do this because it is not based on comparisons. It's like a hash. In this particular case, you work with it by doing bit twiddling operations on the index. So whenever you, in big endian order of that index, whenever you see a 0, you go on the left branch, and whenever you see a 1, you go on the right branch. And so this Radix tree, it has Worse indexing than just copying the whole array, because you just can't get constant time with the tree. Not really. And it has log time update, which is better at this size, but a lot better at a much larger size. And so how does this work in practice? Well, garbage collection cleans up all the old versions. If you don't keep a reference to it, it just gets garbage collected. And garbage collection is pretty cheap these days. And the structural sharing saves a lot of these allocations. And so why isn't this pervasive? Well, as I was saying before, multicore is a relatively new concern. And also, good garbage collection is relatively new. It's much more recent that we have concurrent garbage collectors, where one core can be garbage collecting the memory it cares about, while other cores can make progress. If you've done a lot of work in Java, you probably have noticed that if you have a multi-threaded application, or even a single-threaded application, that it will often just pause while it's collecting garbage. Well, that's sort of a solved problem with certain programming styles, and particularly with this programming style. You can isolate the memory for each thread, and you can do your garbage collection concurrently. So you don't block the whole process, you just block some actor. And the constant or log factors were more of a concern with older hardware, when we were working with much less RAM and much slower CPUs. These days, it's typically worth the trade-off to use a little bit more space and a little bit more time to have a data structure that's simply easier to work with. And in some cases, it's even better than that, because if you do want these branching or undo or redo capabilities, you'll have a hard time doing better than this, both in ease of use and in time and space. So some practical concerns with working with these data structures. For real work, you don't use a branching factor of 2 because you have very bad memory locality if you're allocating memory for like a pointer at a time. So what you do is you just have many more branches in that internal structure. So a common thing to do is to use a big number, like 32 as a branching factor, which is a whole lot better than 2. In particular, if you think about the real sizes of data that we work with, like let's say you have an array with 1 billion elements, right? With a branching factor of 2, that's a lot of branches that you have to walk through to get there. But if it's 32, then it's like 6, right? And then if you take it to 10 billion, then it's 7, right? So you can think of that more or less as constant time, because for any number that you would actually work with, it's basically bounded by 10 or whatever. So it is quite efficient. Even though it sounds like log time is bad, it's actually not that bad if you have a high branching factor. And so how do you actually use this to implement undo? Well, you just keep some data structure that stores every state of the world that has ever happened, or like the ones that you're concerned with. And it sounds like that would be bad. Like, okay, so I have like all the memory that my code allocated, and then I have to copy it all? Well, you don't, because you're sharing structure. And unlike working with mutable data structures, where you have to implement undo and redo as essentially serializing the work that you would do. So if you wanted to implement undo for setting an array, you would have to do the bookkeeping to keep track of the action to undo that. So say I was setting that index from -1 to 0, so I have to have some data structure somewhere where I store the fact that to undo this operation, I have to set the 0th item of this array back to -1. And it turns out that you can actually end up storing more information in that redo log than you would have just simply using immutable persistent data structures to store the state in the first place. And the other nice thing is that once you have these immutable data structures rolling back and forwards in time, you can do that in constant time. So if you have this list of actions to undo or redo, if you want to go all the way back to the beginning or the middle, then you have to replay all those actions in order. Maybe those actions are expensive. Like you could imagine working with like a Photoshop or something, and you have some very expensive operation. You might not want to redo that every time you go back and forth in history. But if you have this structure sharing, you can just jump to any point, and you just have the state. You don't have to replay all those actions. It doesn't work in every use case optimally. Photoshop was probably a bad example because the actions are typically smaller than the structures you're working with. But it is much easier to implement this way. You don't have to worry about testing that code to roll it back because there's nothing to test. You have that precise state of what it used to be. And there are plenty of more optimizations that you can go down when you're working with these immutable data structures. So a very common one in languages like JavaScript or Java or what have you is you can actually use object identity to check for differences in constant time. So if I have some state of the world here and some state of the world here, I can know if they're the same just by doing a pointer comparison. You do a little bit more work to see if the objects change along the way. But it turns out that this makes it very easy to write certain kinds of code. These compares are very fast. So a common example is you have like a DOM tree or something, so like HTML nodes. And you want to render the whole page, and you want to see what changed. Well, you just simply do a walk of the tree, and then you compare the two to see if this child is different than that child by pointer comparison. You don't have to do a deep comparison of the entire tree. You can simply stop at the child node if it is identical to the previous one. And there are more implementation considerations that you can work with in various programming languages and libraries that implement these data structures. They often have like a trapdoor that you can sort of go into and work with the data structure mutably, and when you come out, you have a new instance with different object identity. So Haskell has this with the ST, the strict state transformer, where you can sort of do I/O-like actions, but have a pure interface around it. And Clojure has transients, where you can work with these vectors and maps and such in a mutable fashion. And then when you're done, you just say persist, and then it gives you the immutable persistent version of that data structure. And the JavaScript library immutable.js has a with mutations method where you can do the same sort of thing with these JavaScript versions. And there's a ton of information out there available on this topic. Here are just some selections that I have found utility in. There's a very good video recently at the React.js conference by Lee Byron at Facebook on immutable data in React. And these are all links, obviously, but the URL's at the end of the presentation here. There's standard books on algorithms, and there's a very good book on purely functional data structures. And if you don't want to buy the book, there's a version of an older version of the book that was his PhD thesis that you can just download and read. But if you want to learn how to build functional data structures and how they're designed, that's a particularly good place to look. And if you just want to apply these sorts of data structures, here are a selection of JavaScript libraries, immutable.js and Mori. There are libraries for just about any programming language, but I only had so much room on this slide here. And if you really want to see what it's like to work in an environment where you have mostly persistent immutable data structures, I would highly recommend studying Haskell, Erlang, and or Clojure. These languages utilize immutable data structures very, very well, and they're just pervasive throughout the language. And thank you for your time. I think I have some time for questions. The slides are up on my website here. The source of the slides is on GitHub. And that's my email and my Twitter. I'd be happy to answer questions here or offline, however you would want to contact me. Thank you. Well, with the type of data structure that I was talking about here, the Radix tree, I don't believe that you can do that very effectively. And it's very hard to do an infinite data structure in this style in a strict programming language, which is most of them. But if you have a language like Haskell in particular, where the evaluation is non-strict, you can very easily sort of tie the knot where the data structure refers to itself. And this is commonly used in like linked lists, for example, if you have a list that you just want to cycle infinitely. But that's I haven't seen too many of those sorts of infinite data structures used in practice outside of Haskell.
Yeah, how far back do you think some of this concepts of persistence data structures will be applied to some of the older languages? I mean, I went and searched and I was looking for, what ways that I could use it in Java, for example, and like how reliable would it be? I found a little bit, but not too much. I was wondering if you might know sort of to what extent it's sort of available to older languages.
So, I mean, first of all, it doesn't really have anything to do with the age of the language. It was really the design philosophy. So the question was, can I find persistent, immutable data structure libraries for older languages such as Java? So, like, Haskell was born in 1990, and Erlang was born around the same time, and I believe that's a couple years older than Java. So the age isn't so much of a factor here. It's just what people are using it for. So I don't do a lot of pure Java personally, so I don't know off the top of my head which libraries you should be looking at, but I am absolutely positive that they exist because two languages that have very good persistent data structure support are built on the JVM, Scala being one and Clojure being the other. So I suspect that those data structures should somehow be accessible from Java, or some equivalent should exist for Java. You may find these data structures hiding in, say, like a concurrency library, for example, because you often want to work with these sort of lock-free or immutable data structures in that kind of environment. But I can't speak to the quality of any particular Java library, but that would certainly be something good to know because it's a very useful language. Python, I haven't seen such a persistent data structure library in common use in Python. It just so happens that the constant factors to do almost anything in Python are very, very high. So you have to really, really want something like this, and it turns out to not often be the right trade-off in Python in particular. The constant factors I'm talking about are the size of an object is pretty big, and the cost of a function call in Python is quite high. So when you're doing Python, you tend to use data structures that are implemented in C that have very sort of thin Python bindings, rather than developing your own Python data structure, because the constant factors are just so high if it's pure Python. So I've seen a couple, like, maybe medium to low quality libraries for this, but I haven't actually seen them in use. But I haven't looked that hard.
Would a backdoor mutability library for C++ or C be like atomic, where it wouldn't affect like multiple copies of the same object?
Yeah. So typically these sort of mutable backdoors, they work with like a copy on write sort of philosophy under the hood, and then so it would be atomic, because you don't actually directly mutate the object that you are using that backdoor on. You sort of mutate a view of that object, and then when you say you're done, then it creates a new object afterwards. So it's a totally safe thing to do because the mutations are completely local to that like call stack that you're working with, and you're not stomping over any of the existing memory that was allocated before.
What's the ideal number of cores, in your opinion?
Well, I think that the ideal number of cores really depends on what you're trying to do. I mean, with the way that programs are written now, it would be ideal to have maybe 2 cores and just make them really, really fast. But the laws of physics make that impractical. So we really should have more cores, but we need to do a much better job as computer scientists and software developers at figuring out how to use them all effectively. And that's something that just isn't commonly done these days. There's a lot of research in that area, like how to take advantage of 64 cores or 1024 cores, and we're starting to see hardware coming out of like Intel Labs that has thousands of cores on a single chip. And we do a limited version of this like very parallel programming when we work with GPUs and technology like that. But the tools for doing general purpose programming just haven't caught up to the amount of cores that we actually have in devices today. I mean, who wouldn't want to have more? But we really need to do a lot of work to make it effective to have more cores, because right now I think the more cores you have, the less likely you are to utilize them. They would just be sleeping. But if you have good technology to have them not consume power while they're sleeping, then that's fine, I suppose.
Do you have any sense of the real-world application of this? Here's what I'm thinking about. Many years ago, I worked in an environment where we had to poll a bunch of devices to see if they were online. Mm-hmm. The fastest way was to go out and poll them all at once. But the result was the user noticed this pause. And so when we distributed the polling out to the rest of the processing, it took longer for the processor time, but the user thought it was faster. Mm-hmm. So do you have any real-world sense like that, how this works?
You do sort of see a lot of that. So the question was, in the real world, how do you see these data structures being used? So the example that you gave is actually a really good example, such that you had this serial polling process where you polled a whole bunch of devices before you would update the display to the user. So if you were doing that with a persistent data structure, what you could do is you could take subtrees of the list of devices to poll, and then you would fork off actors or threads or what have you, whether it's on the local machine or other machines, and you could update them all you could do all the polling in parallel, and as soon as the poll comes in, you would replace the state of that subtree with all those polled devices. And then the user interface, it would see a new state object, and then it would just walk down the tree to see what changed, and then would just update that part of the scene graph, whether that's DOM or OpenGL or what have you. So I've certainly seen that sort of approach taken, and it tends to work quite well in my experience.
Any questions? One last question. You mentioned efficient garbage collection. What do you mean? Was garbage collection ever efficient?
Well, So by efficient garbage collection, I'm really talking in relative terms. Obviously, if you can manage to not do any garbage collection, that is ideal, of course. But with the programming languages we have today, we don't really have the option to go the other way, where you don't have garbage collection. I mean, you see a bit of that in C and C++, but in reality, people end up using like reference counting or something like that, which is sort of like garbage collection, and it has a lot of that bookkeeping overhead. If you could do this in a, what is it called, like linearizable environment, like Rust or something, where you actually keep track of ownership through the call stacks, and you can allocate precisely the amount of memory that is necessary, and then immediately discard it without any sort of actual collection process. That would be better, of course, but I think that's still sort of an active area of research and not something that people use much today. But with regard to efficient garbage collection, it has gotten just so much better over the past, say, 20 years. And in more recent years, we have concurrent garbage collectors where you can have a separate core doing the garbage collection from the core that you're making progress on, which you know, it's still using more CPU time and temporarily more memory than a non-garbage collected approach, but that turns out to be okay because we're typically bad at using all the cores anyway. So keeping one busy doing garbage collection is not really a bad trade-off today.
Any other questions? Well, thank you.